the last class we discussed about the small signal model of the MOSFET amplifier, and we found out the amplifier parameters like input impedance, output impedance, voltage gain, etc., using that small signal model. But one thing which is important and that we ignored is that in that small signal model which we developed, we ignored the capacitance effects. In fact, there are capacitances present in the MOSFET device, and we have to consider these capacitances when we want to see the frequency response. That means, if we want to know about the gains when the frequency is low or very high, then the capacitances have to be considered. As we earlier also in BJT amplifiers considered the junction capacitances which were present in the device and incorporating them into the small signal model, we derived the pi model. Similarly, here also in the MOSFET device, because of the capacitance effects being present in the device, we will have to consider these capacitances when we try to find out the frequency response, that is the gain in the high frequency region and the low frequency region. Now, the internal capacitances which are present in the MOSFET device are because of the structure of the device. Now, let us see how the structure of the MOSFET device brings those capacitance effects. So, for that we will have to go back and see the physical structure once again. So, let us recall the physical structure of the MOSFET device. Here we have a silicon dioxide layer in between the gate and the substrate, and this insulator which is present is basically forming a parallel plate capacitor between the gate and the body or the substrate. So, as we know that in between two parallel plates having an insulator in between, there will be a capacitance, and because of this insulator having the dielectric is in between the gate and the substrate or the body, there will be capacitances between the gate and the source as well as the gate and the drain as well as the gate and the body. So, we have three capacitances coming into existence because of the presence of this dielectric in between the gate and the substrate. So, let us name these capacitances which are present between gate and the source, gate and the drain and gate and the body as CGS, CGB and CDB. Now, these capacitances we will have to incorporate into the model which we have earlier derived. So, the three capacitances which are coming because of the gate is due to the gate electrode forming a parallel plate capacitor with the channel having oxide layer silicon dioxide in between them. It is like here we are having, this is the oxide layer in between the gate electrode and the body, or the gate electrode, and this is the gate electrode and the channel, the whole channel if we look into. So, here this is the gate electrode and this is the source, in between them there is this oxide layer. Similarly, this oxide layer is extending. So, it is forming a parallel plate capacitor between the gate and the channel. The channel is having these three regions. One is the drain, source and the body itself. So, in the region between the gate and the source, because of this oxide layer, there will be one capacitance here, that is C gate to source capacitance. For this drain, because from this gate electrode to this drain, in between we have the oxide layer. So, that will be C gate to drain, and from the substrate to the gate again there is this oxide layer. So, that will be having C gate to body. Apart from these three capacitances, we have another type of capacitance, which is there between the source and the body and the drain and the body because of the depletion layer. Now, if we look into the structure of this MOSFET device, there is a p-n junction in between the source and the body. Because this body is made of P, we are considering a MOSFET device which is having a P type substrate. So, it is an N channel MOSFET we are considering. So, in between the source and the body means the substrate, we have a p-n junction. Similarly, a drain is having a p-n junction between the substrate and itself. So, there are two p-n junctions. Now, these p-n junctions will be having the depletion layer capacitance, and that depletion layer capacitance in the p-n junction between the drain and the substrate or the body is known as drain diffusion, and the p-n junction depletion layer capacitance between the source and the substrate or the body is the source diffusion capacitance. So, we have, because of the presence of this depletion layer in the p-n junction formed between the drain and the body as well as the source and the body, the drain diffusion and the source diffusion capacitances will be present. So, now because of these depletion layer capacitances, we have two capacitances which are named, suppose as CS to be source to body capacitance and C drain to body CDB capacitance. So, in all together we have now 5 capacitances which are the capacitances in the MOSFET device. So, we will have to consider these internal capacitances of the MOSFET device. If we want to exactly draw the small signal model, and this will be this will be very important in order to know the response in the high frequency region, because in the high frequency region these internal capacitances will be dominating, and of course in the low frequency region also there will be capacitance effects, but these capacitances are due to the coupling and bypass capacitors in the circuit. But these internal capacitances will be affecting the response when we consider the high frequency region. So, as we have found earlier in the BJT amplifier, because of the capacitances being present in the amplifier circuit, we have a response. That means, if we find out the gain versus frequency, it is not constant gain, but it drops off in the low frequency and the high frequency regions. In the low frequency region, the gain which you get in the mid band frequency region, which is constant, that will be dropping off due to the external capacitances present in the circuit, like coupling capacitor and the bypass capacitor. And in the high frequency region, when we consider that the frequency of the signal being applied at the input is having a high frequency, then the internal capacitances which we have just now described, they will be affecting the gain. The gain will be reduced. So, in low frequency as well as high frequency region, the gain of the amplifier drops off. So, we get a frequency response having a gain constant in the mid frequency region, and in the high frequency and low frequency region it will be dropping off like this. So, if we plot the gain versus frequency, if we suppose find out the voltage gain, then at the mid band region the voltage gain will be constant. This is the mid band region, and in the frequency when it is very low and very high, it will be dropping off. This dropping off is because of the capacitances which are present in the circuit in the low frequency region, and because of the internal capacitances in the high frequency region. And we know that there is 3 dB frequency, which is a very important one, and that is when the gain drops off to 1/√2 times the mid band gain. We get lower 3 dB and higher 3 dB frequencies, these two frequencies that are cutoff frequencies, and all these considerations we have already discussed while discussing the BJT. So, similar characteristics we will be obtaining here. So, now the small signal model which we will be getting when we consider these internal capacitances will be like, in addition with the components which are in the small signal model, we will have to augment by incorporating the internal capacitances. The small signal model components which are there already that we have derived, like we have the current source given by GM VGS, as well as drain to source resistance RD. Apart from these components, we will be having now these capacitances which are the internal capacitances, and we will have to incorporate these capacitances in the small signal model. Then we will be getting a pi model. So, that we are going to draw now. So, we have already have this small signal model, and in this small signal model these capacitances will be incorporated, but now we will be considering 3 terminal device, which is mostly done in practical circuits. 3 terminal MOSFET means we have the body and the source being connected. So, if the body and source is connected, which results in a three terminal device, then our job will be much simpler, because instead of the 5 capacitances which we have now got, all these will be not applicable, because the body and the source terminal is the same terminal, they are connected. So, what will happen is that the source to body capacitance will be simply vanishing, as well the gate to source and gate to body, these 2 capacitances will be only one capacitance from gate to source. So, now we will be getting a small signal model when the source is connected to the body, as shown here. We have this current source as well, the RD we have already got in the small signal model which we discussed for the mid band gain. Now, we are having the gate to source capacitance. So, this is the capacitance from gate to source as is shown here. Then gate to drain capacitance, that will be connected between gate and drain, and there will be a drain to source or drain to body capacitance. Drain to body capacitance, which we have seen that because of the PN junction which is having the depletion layer. So, this capacitance between drain to body will be there. So, we have extra 3 capacitances in the small signal model. Now, we can further simplify by ignoring drain to body capacitance, which is done in some books. So, then we will be having only the 2 capacitances, gate to drain and gate to source. So, this model, which is the high frequency model, will be now plugged into the actual amplifier circuit, and the response of the amplifier can be obtained. Of course, the computations etc. will be much complex now, and it can be done easily in PSpice, not manually, because we are having now many computations to be performed. So, if we now plug in this model into the amplifier circuit, draw the AC equivalent circuit, for example, for a common source MOSFET amplifier, then the AC equivalent circuit for common source MOSFET amplifier will be having these capacitances as shown here. We are, for the timing, we are now ignoring the drain to body capacitance. Just for simplicity, we are showing these 2 capacitances. Now, if we look into this circuit, which reminds us of the circuit that we considered for BJT amplifier in the high frequency response case. So, here actually we are having a capacitance between gate and drain CGD, because of which this circuit is posing a problem for analysis. If we can somehow bring this capacitance into either the input and output circuits or both by using some theorem, then we will be having easier analysis, because then the input and output circuits will be isolated, because this is the component which is the capacitance between gate and drain, that is basically having a contact between the input and the output terminals. So, here we will be taking help of the Miller theorem. So, if we remember Miller's theorem, what we used to do is that we were basically distributing this capacitance into input and output circuits, then we will not have a capacitance in between gate and drain, but we will be having capacitance in the input and output circuits, which can be combined with the capacitance which are already present. So, that can be done, and the analysis of this circuit will be following in a similar manner as we are earlier doing using Miller's theorem for BJT case. So, this Miller's theorem is used for finding the voltage gain. In the high frequency region, you will be finding the voltage gain by using Miller's theorem to find the overall capacitance by distributing the capacitance C, G, D, gate to drain capacitance, bringing it to the input or the output side. So, this can be followed in a similar manner. So, we will not go into again repeating that analysis here, but this analysis can be easily followed as we have earlier done in BJT. So far we have been discussing about the MOSFET device, and this MOSFET device is having its name because we have seen in the construction that there is metal, there is an oxide and semiconductor, all are there in the device. Now, there is another device which is also a field effect transistor or FET, and it is the junction field effect transistor, that is JFET. So, we will be now discussing about the JFET, because we have been discussing MOSFET, we have seen the enhancement type, depletion type MOSFET devices. Now, JFET is also a field effect transistor. It is a simple FET device. It has also high input resistance, because in MOSFET we have seen that the input resistance is very high. The JFET is also a device which is having a high input resistance, but this input resistance of the JFET is in fact less than the input resistance of the MOSFET. And also there are some other advantages of the MOSFET device, because of which actually the MOSFET is gaining popularity, and this JFET is going to be obsolete day by day. But still we will be discussing JFET a little. So, let us now see the structure of the JFET. The physical structure of the device is having a N channel, that is a semiconductor which is N type, and there are two P type semiconductors as shown in figure. There are metal contacts as shown here. This is actually, these are the metal contacts, and from these metal contacts we draw out three terminals which are known as the drain terminal, gate terminal and the source terminal, as earlier in MOSFET device also we have got. And here these two P which are having the metal contacts are connected together. These two P's are connected together, and the gate terminal is drawn out from these two metal contacts. That means we have the gate terminal which is having a contact with this P as well as this P. As we can see that the same lead is connected to both the P through this metal contact, and that is the gate terminal. And there are drain and source terminal. we are considering here an n channel JFET. Now, this is the channel which is the n channel, this is the n type semiconductor. Now, in this structure, as you can see here, this is having n type material which is rich in electron. So, electrons will be abundant in this n channel, and this channel n channel it is, and there are two p type semiconductors. So, if we now apply a positive voltage VDS, that is, we are having D, the drain, at a positive potential with respect to the source, and we do not apply any voltage between the gate and source. Then what will happen? Suppose this is the condition where we are having no voltage between gate and source, only we are having a positive voltage between drain and source, and in order to simplify the diagram, these two p type materials which are connected to the gate, we are not showing this common connection. Actually, there is a common connection between these two p, but instead of that we are just showing a gate terminal here also. It means that this is also gate terminal, because these 2 points, these 2 p's are connected by these 2 metal contacts, and this lead is connecting between these 2 metal contacts. So, these 2 p's are having the same gate terminal, which is described by writing a G here. This is also G, this is also G. We are now not applying any gate to source voltage. That means gate to source voltage is now 0. There is no potential being applied between the gate and source terminal, but there is a positive potential at the drain with respect to the source. Now, what will happen is that if we apply the VDS positive, of course, VDS has to be kept at a low voltage. We should not increase the VDS, because if we go on increasing the VDS, that will be having another effect which we will be discussing later. Right now, let us assume that we are applying a small positive voltage between drain and source, and gate to source voltage is 0. That is simply like gate to source terminal is being short circuited. Now, because of the abundance of the electrons present in the n channel, these are electrons present, they will be attracted by the positive terminal of this VDS. So, there will be flow of a current between drain and source. The conventional direction of the current is from top to bottom, from drain to source, as shown in this arrow mark. As electrons are moving from source to drain in this direction, so the current direction is opposite to it, which is the conventional direction of current, that is the drain current. It is called from drain to source. So, the same current will be now going out from the source terminal and ending at the negative terminal of the VDS. So, this completes the current part. So, the drain current is equal to the source current. So, this is clear that we are not applying any gate to source voltage, even then the current will flow from drain to source because of the attractive force due to the VDS on the electrons in the channel. Now, of course, we are keeping this VDS small. When it is very small, the current will be small, but as we increase a little, it will be like an ohmic contact, like in a ohmic device, which is current increases linearly. So, initially if VDS is small, for the smaller region when we increase a little, it will be increasing the current. Then if we go on increasing the VDS, then another phenomenon will occur, which is the saturation or pinching off, that we will be discussing. But next let us now apply a negative potential between gate and source. Now if we are having a gate to source voltage which is negative, drain to source voltage is positive, what will happen? There is a depletion layer between the P and N as well as this P and N. This depletion layer, depletion region or depletion layer width will be dependent upon the reverse voltage being applied. Now which one is the reverse voltage? As we are having a negative voltage between gate and source VGS, and by this variable arrow mark we are meaning that we are changing the VGS, that is gate to source voltage is say varied. Initially it was 0, what we have seen earlier. Now it is increased a little. If we go on increasing, what will happen to the width of the depletion region? It will be increasing, because as far as this P and N is concerned, if we see that we are having this gate to source voltage negative, P is connected to negative and this N which is connected to positive. So this is a reverse biasing voltage. This reverse, due to this reverse biasing voltage, if we increase this voltage, this depletion region, it will be increasing. So in between the P and N region, whatever depletion region is there, depletion layer, which is the region where you have the immobile charges only, that region will be increasing if we increase the reverse biasing voltage, that we already know. So now when this depletion region increases, here also it is now it will be increasing to a broader depletion region, here it will also be increasing to a broader level. Then what will happen is that the channel width will be narrower and narrower. So now width of the channel is narrower, means the current, the drain current will be going on decreasing, because the drain current is dependent upon the charge carriers present in the channel. Now the channel is narrowing down, means what? Lesser charge carriers will be now available to flow. So the current between drain and source will be reducing. Now if we go on increasing the VGS, then at a point what will happen is that the channel will be totally bereft of charge carriers and the current will be 0. So that voltage between the gate and source in the negative region, or the negative gate to source voltage at which the drain current becomes 0, is called the pinch off voltage. It is like the threshold voltage in the depletion type MOSFET. So in the depletion type MOSFETs also we have seen that there is a threshold voltage below which the gate to source potential should not go, because then the current will be 0. So similarly here this pinch off voltage is that voltage between the gate to source, it is negative, mind it. So that at that voltage where the drain current becomes 0. So in order to have a drain current flowing, we must have gate to source voltage greater than that pinch of voltage. So, every JFET device will be having its pinch of voltage specified. So, now if you go on varying gate to source voltage, then it will be going on, the current will be going on reducing and reducing, and it will become 0 at when it reaches the pinch of voltage. Mind it, we are not changing the gate, the drain to source voltage, the drain to source voltage is constant. So, basically what is happening is that the gate to source voltage is having a control on the drain current, the control being effected via the gate to source voltage. So, when we have this gate to source voltage negative, we are having a hold over the drain current, because drain to source voltage is not changed, it is constant voltage we are applying. Now, what will happen if we keep gate to source voltage constant and vary the drain to source voltage? Next, let us discuss that situation when we have a constant negative gate to source voltage, but drain to source voltage is now varied. So, drain to source voltage, which is having the polarity as shown here, this is positive, this is negative, that means drain is at a positive potential with respect to the source. What will happen now is that initially when we have a smaller drain to source voltage, the current will be increasing along with the increase of drain to source voltage, almost as in a linear region, because it is like an ohmic device only now, because the n channel resistance will be defining the current, and you go on increasing when the VDS is small, an increase of VDS will be giving a more force on the electrons in ion channel, so current will increase. But then if we go on increasing the VDS to a high value, what will happen is that the channel between these two P's, that n channel which is present, this n channel will be having a change in its width, because one phenomenon which is happening here is that the depletion region which is present in the PN diode, that is this in between the PN materials, this depletion region is dependent upon what? Upon the reverse biasing voltage. Now, as we increase the VDS, the reverse biasing voltage which is present between the gate and the drain will be changing. When the when we have a small VDS, then whatever was the region width in the depletion layer, that will be not same when you increase the VDS, because increasing the VDS means that the reverse biasing potential for these PN diodes or the PN materials will be now increasing towards the drain side. If we go on increasing VDS, because gate to drain potential is dependent upon this drain to source potential. So, gate to drain potential is important, because on that the width of the depletion layer will depend. So, if we go on increasing VDS too much, then the depletion layer width will be increasing and increasing, and the N channel will be having a modulation in its width. It will be tapering towards the drain side. That is, the width will be maximum at the source side and it will be tapering or narrowing down towards the drain side, because at the drain side the reverse biasing potential for this Pn is maximum. So, this is due to the increment in the VDS too much. So, what will happen is that if we go on increasing VDS, a point will be reached when the N channel will be having only a point of touch at the drain side. It will be almost like it will be touching at the drain side, it will be like this. So, when this happens, it is also like a pinching off phenomenon, that there will be saturation of the drain current, and that is why when we go on increasing the drain to source voltage, the drain current will be reaching a point of saturation or pinching off, and beyond that, even if you go on increasing the drain to source voltage, the current will be remaining constant at the saturation value. So, this phenomenon is similar to the pinching off that we discussed in MOSFET. So, it is due to this reverse biasing potential between gate and drain being varied because of the variation in VDS. Because if you look into the two terminals gate and drain, which are having the N and P, the drain is having this channel N, this drain is having this N, and this gate is having this P. So, the depletion layer depends upon the potential between the gate and drain. The drain is positive, gate is negative. So, that means we have now VGD, which is basically the determining factor. Because of these phenomena happening in this JFET, for variation in VGS as well as variation in VDS, keeping one constant at a time, we can now draw the VI characteristic. Now, one thing to note is that when VGS was 0, the current which was flowing between drain and source, due to the presence of the small positive voltage between drain and source VDS, that saturating value of that current is known as idss. Idss is the current which is the maximum current or the saturating or the pinching off current that is flowing in the device when we have gate to source voltage 0. Because we know that because of this phenomenon of pinching off, what is happening is here, if we go on increasing the VDS, a point will be reached when we have the saturation or pinching off. Suppose at this point it is pinching off. So, this maximum current ID is known as IDSS for VGS is equal to 0. So, this current, this is the IDSS. So, this current IDSS has the maximum value for this Vs is equal to 0, and you have in MOSFET device, this is JFET device, this is specified, the idss will be specified. Now, in order to draw the Vi characteristic, we have to just map all these regions, likewise as we have done in the MOSFET. For JFET device, here these regions are, as we can see here, VDS is positive and this is the corresponding ID. Now, for different values of gate to source voltage starting from 0 to negative, we are plotting this. Now, one point is important here is that you cannot apply Vg as positive, because if we have Vg as positive in this JFET, if we have Vg as positive, we are applying suppose a gate to source voltage positive, then the current will be not controlled by the gate to source voltage. The gate to source voltage will be losing its control over the drain current. It will be simply, if we now visualize that if this gate and source is having a positive voltage. So, it is P, it is N, this is positively connected, that means it will be current will be increasing and it will be not controlled, it cannot be controlled. Only when VGS is negative, it has a hold over the drain current, because by modulation of the depletion layer in the PN, the current is controlled. So, unlike depletion type MOSFET, which had the depletion region as well as the enhancement region, that means we could give VGS positive also, but that is not possible for this JFET device. It is always only operated when VGS is negative, and the maximum value of VGS you can give it 0. We cannot give positive voltage, that means we cannot go beyond VGS is equal to 0. So, now the Vi characteristic can be plotted by mapping all these regions into the ID versus VDS curve, and as we have discussed, when we have VGS less than the pinch of voltage, magnitude of VGS is less than the pinch of voltage, then it will be current will be 0, drain current will be 0. So, this is the line, because here for this example we are taking that pinch of voltage is equal to minus 4 volt. So, if VGS is less than minus 4 volt, then obviously the drain current will be 0, and that is shown by this line. The line which is just coinciding with the 0 line on the VDS axis, that is the cutoff region, that is called cutoff region, the device is turned off. Now, we have VGS is equal to 0, then we get this curve. So, this is the maximum current, that is the saturating current when VGS is equal to 0, and that is known as the idss current. This is the drain to source current when VGS is equal to 0. And now, if we go on increasing the VGS, say VGS is equal to minus 1 volt, minus 2 volt, minus 3 volt, this way, then the current will be reducing and reducing because of the depletion region being increased, the channel width being reduced. So, the drain to source current will be reducing, and that is just reflected in these plots, that the current will be now, drain current will be reducing if we go on reducing the VGS, that can be seen here. And when we reach the pinch of voltage by reducing the gate to source voltage, then we get totally 0 current. And if we now increase the drain to source voltage, as we have seen here, the current will be reaching the pinching of our saturation region. So, in this region is the saturation region, this is the saturation region where we have the condition that drain to source voltage is higher than gate to source voltage minus pinch of voltage. and here also it reminds you of the depletion type MOSFET. There it was the condition for the saturation of the drain to source current, which was when the drain to source voltage was greater than gate to source voltage minus the threshold voltage, and that threshold voltage has a counterpart here, which is the pinch off voltage. It's otherwise it is the same characteristic. And when we have these two voltages equal, then this is the locus of this points when VDS is equal to VGS minus VP. So, this curve is actually plotted from the points of the saturation, that is the saturation point when it reached. So, as we go on increasing the VGS from say bottom to top we are going, then the saturation is shifting towards right and right, at a more voltage the saturation is happening. And when the drain to source voltage is less than VGS minus VP pinch off voltage, this region is known as the triode region. So, we have cutoff, then triode, then saturation regions, these three regions. And one important thing, as we have mentioned, that VGS cannot be positive. So, we do not have an enhancement region as we were having in enhancement type of depletion type of MOSFET. Depletion type of MOSFET we are having two regions, depletion as well as enhancement, but the JFET does not have the enhancement region, means we do not have the region when VGS is equal to positive, that is not possible. So, here that this characteristic curves give us the idea about how we can control the drain to source current by changing the gate to source voltage in the negative way. That means, if we apply a negative voltage between gate to source, we can control the drain to source current. If we go on increasing gate to source voltage, the drain to source current will be going on reducing. And next, we draw the symbol for the JFET. So, this is the symbol. We have two different types of JFET, N channel and P channel. N channel is having the channel made of N and 2 P type. Similarly, in the P channel, the channel will be made of P and there will be 2 N type regions. So, the symbol is as shown here for the N channel and this is for the P channel. The drain current direction will be reverse for the P channel, because we will be accordingly applying the polarities there in the P channel. Now, the direction in the arrow from the gate is actually indicative of the direction of the current in the channel. If it is N channel, the current will be from the P region to the N region. So, the gate will be having a direction of current as shown here, because if we look into the device structure, this is P and this is N. So, from P to N current flows, that is indicative of the arrowhead in the gate terminal. Similarly, if it is a P channel, that means the channel is made of P. So, you will be having current from P to the gate. P to N means P to the gate. So, this is two are symbolic representations for the two types of JFET, and it is meaningful in that way that you can know about whether the channel is N or P by simply looking into the arrow. And the current which flows in the device from drain to source, this ID current, is given by an important equation known as Shockley's equation. This is Shockley's equation, which relates the current with the voltages as this equation gives you the value of the drain current, which is given by IDSS into 1 minus VGS by BP whole square. So, VGS is the gate to source voltage, BP is the pinch off voltage. So, it will be whether VGS negative or positive, and we have seen that we generally will be having only negative voltage, because VGS is always given a negative voltage, and pinch of voltage also has to be negative voltage. So, the current equation can be used for finding out another important parameter, which is the transconductance GM. Now, here this IDSS and VP, these two are important parameters for the particular JFET device under use. That means, if we are using a JFET device, we must know what is the value of the pinch of voltage and the IDSS current. So, these will be generally given in the data sheet. Whatever device you are using, JFET device, that will be having the values of the pinch of voltage and the IDSS written in the data sheet. So, these two are known for a particular JFET device which we are using. So, if we know these two, depending upon what gate to source voltage we are applying, we can find out the drain to source current for that gate to source voltage. And it is a square which is signifying the non-linearity of the curve. It is not a straight line, or it is not having a straight line equation, it is having a non-linear equation given by this square term, and that is very obvious. We could see in the plot of current versus voltage that it is a non-linear curve only. The value of ID, as it depends on IDSS. And now, if we consider the drain to source voltage, now the drain to source voltage should be such that it will be making the JFET device current or ID current in saturation. It will be in saturation, and the saturation region is generally used for amplification, like we have seen in MOSFET. So, today we have discussed about one important phenomenon in MOSFET device, which was the small signal model having the internal capacitances which are coming because of the construction of the MOSFET device. And because of the internal capacitances being present in the MOSFET device from gate to channel as well as from drain to body and source to body, we have to consider these capacitances and incorporate in the small signal model, and using this pi model or the small signal model having the capacitances, we can find the high frequency response, and the voltage at the high frequency will be reducing than the mid band voltage gain what we studied in BJT also. And next we have started discussion on one FET device, which is the junction field effect transistor. We have seen the VI characteristic, and next we will be discussing how to use this JFET in actual amplifier.